The Coding Competence Center is a technology platform where we develop solutions and where we demonstrate that we can scale up the solutions which we have developed in our lab-scale research facilities, and often we do that together with our industrial partners to demonstrate that it's also applicable for industrial use. We are always proud if we can pave the way for product innovations. Since 2016, we have, for example, produced new solar cells with efficiency records. We have enabled new battery designs for solid-state batteries. The mission of the center is to demonstrate that we are actually able to upscale what we have done on a lab scale and produce it in a way with standard processes which are also used in industry. We demonstrate that we can fabricate and produce the next generation of products which are necessary for meeting the demands of the society.
The Coding Competence Center at Empa is a public-private partnership, so it allows us collaborating with various stakeholders, starting from collaborative projects more for academic direction, as well as direct projects together with industry. Covering this whole value chain allows us to be really flexible and effective when addressing scientific questions.
If you are looking at an invention in the laboratory and the effort it needs to bring it to a market, then we need a lot of competencies. The CCC actually unites all these competencies, including also industrial partners.
Having state-of-the-art equipment which is representing what we actually will find in industry is very important for us to be able to work on a level where we can meet industrial requirements but also push the limits for the next generation of products.
The Coding Technologies Group develops advanced processes for new thin film materials for a variety of applications. We develop hard coatings, but also other applications like semiconductors or even piezoelectric thin films. The Coding Technologies Group has a strong collaboration with Oerlikon Balsas, and as part of that collaboration, we operate an Oerlikon Ingenia sputter coater that allows us to scale up our processes from the lab to industrially relevant scales. Scientifically, it's very exciting because it's a non-equilibrium deposition technique, so it allows us to access metastable phase space. We can deposit films that are very hard to make with other techniques. And then it's also quite interesting because it's very established in industry already, and a lot of what we develop in the lab can very easily be scaled up. We perform a lot of process development in high PIMs. High PIMs is a highly energetic sputtering technique that is traditionally used for hard coatings. You can get very dense films of high hardness, but at the same time, you might incorporate some process gas. We are now trying to use this technology for different types of applications that are much more defect sensitive. With complex deposition processes, the research questions are highly technical and involved, so you need to bring together a team with physicists, material scientists and chemists to really drive the innovation from the process development to the finished thin film material.
At Empa, one thing we are part of is the European project 2030+, which is looking at stable, sustainable and affordable batteries. And there we have various streams, one being solid-state batteries, next generation lithium-ion batteries and also sodium-ion batteries. One thing we are very proud of is our autonomous robot battery development platform, which is able to synthesize the battery material, to assemble the cells, to run cycle, to assess the performance, and then use the data in order to make a prediction what to test next. So we are able to do the full cycle in an automated manner, which enhances the way and the speed we are developing new batteries. At Empa, we do fundamental research. We have a lot of analytical devices, but we also work closely with the industry, so we understand what are challenges when it comes to production.
So the thin film solar cells are called thin film solar cells because the thickness of the active layer is on the order of few microns. And the unique advantage of thin film solar cells is that they can be deposited on flexible substrates like plastic foils or metal foils, and thin film photovoltaic modules can be used in applications which require flexibility or lightweight. So we have developed a special method for making transparent conductive contact of the thin film solar cells. This is a critical component of any thin film solar cell because it allows the light to pass into the cell and at the same time it collects the photo-generated current. So it was certainly a collaborative effort of postdocs, very motivated PhD students and the help of our industrial partners, which guide us what are their industrial needs and what are their regulations and what are the expected costs of these newest processes.
Printing and wet coating methods can of course be used in everything in the world, but here I would like to focus on printed electronics. This is printing functional devices using functional inks on flat substrates, very much like printing newspapers. Conventional inks have a high amount of additives and they are contaminating these inks in most of the cases. So you have to get rid of those additives once you have deposited the ink on your substrate. And this is a big challenge because it requires high temperatures, perhaps harsh, aggressive solvents. So this is something you want to avoid. Graphene inks are inks that are composed of graphene flakes. Graphene flakes are two-dimensional nanoparticles that you find also in graphite, for example, in a pencil, but it's exfoliated graphite, it's two-dimensional nanoparticles. Printed electronics today is a multi-billion market. Being in this field is therefore of a high importance for Empa, of course, but also for Switzerland.
I would say Empa is really a driver, especially also in battery research, bringing new ideas to Switzerland and collaborate in Europe with the best potential partners.
I think the uniqueness here at Empa is that we encompass all these different facets of technology development. This starts with the inventions made by PhD students, for example, but those inventions are then channelized by our senior scientists into certain directions where technological development makes sense. So we are able to go from the laboratory invention to the prototype that we can discuss with industry.
We hope that we can continue our success stories in certain domains like, for example, solar cells, solid-state batteries, and that we develop something which is really for the benefit of the society so that we can overcome the most pressing challenges we are facing today in the field of energy, mobility or climate.